Let's get started with digital logic. So the content that we are going to discuss right now is in the perspective of GATE, but I will be discussing very briefly about things because it is not possible to discuss it in a comprehensive manner, which will consume a lot of time. But if you are okay, then I will be uh, willing to discuss it again. So now let's see a bit of history first. Okay, before this is number system which is on the screen, but I would be like I'd like to discuss about a small history part, which goes on like around in some 90s or 1880s or something. A scientist called Jack Kilby uh, made integrated circuits ICs on some rocks. So that was the first IC which was made by him. And we also know a thing called JK flip-flop, which is named after that his invention. Then this itself was an invention actually. So that is basically the start of digital electronics. So he is the father of digital electronics actually. So then another scientist named Moore was also a very good observer. So what he did was he observed a lot of things. Like both of them lived during the same era. So Moore could not discover new things or invent new things, but he did have a great observation power. So he observed things, and then he concluded that the number of elements fabricated on a single buffer will be doubled every 18 to 24 months. This is Moore's law, which just by giving this statement, he got Nobel Prize actually. Okay, so let's discuss about digital. So in digital logic, what we have is everything that we do here is in the zeros or ones. The computer cannot understand our language. So here we talk in terms of zeros and ones. You need to understand digital logic in order to understand computer organization and architecture. You need to understand COA to understand properly about OS, right? So it goes on. Digital logic is the base for everything. So in the number system, we have bits. So we have bits. In the sense, bits means zeros and ones, both of them. Then if we have 2 bits, you can call it as a DIT. Then if it's 4 bits, then it's a nibble. If it's a 8 bits, then it's a byte. So remember, in any question, if you get small b, that means it's bits. Okay, if you get capital B, that means it's byte. It's a byte, and 1 byte equal to 8 bits. Okay, remember that. Then we have in the digital and in the data that we usually use, it's different. So you can see this physical quantity. In physical quantity, kilo is 10 power 3, which corresponds to 1000, right? But in digital, a kilo is 2 to the power 10, which is 2 to the power 10 is what? 1024. So it's almost like that. Okay, so the similarly mega, and here also it's like that, giga here is like that. Okay, remember this. Okay, then we have something called base or radix. Okay, which tells us what the digit or the term which is written in what base. Okay, so yeah, so if the base is 2, that is binary, means the digits allowed are zeros and ones. If it's 3, then you can write up to 2. If it's 4, you can write up to 3. 0, 1, 2, 3. Similarly, there's an octal system, octal representation system, where you start from 0 till 7. Then we have hexadecimal. So in hexadecimal, what you do is you go till 9 but not write 10 because 10 becomes 2 digits. So you write A, B, C, D, E, F. Okay. Yeah. Then we have some another concept which you should be wary of is that whatever thing you write here, suppose this is 12C. So here the maximum is what? C. C corresponds to what? 13. So 13 is the minimum base. If you write something else, that is, see in this example, it is 258 base 8. Base 8 meaning you cannot write any digit which can surpass 8. So if you write that, it's not a valid representation, so it's wrong. So then for every digit that you write, this is called the radix, the base, and this to the extreme left is called most significant digit, MSD. Okay, then this is a least significant digit, LSD. You can also, some people also call MSB or MSD, LSB, right? Most significant base and least significant base. Okay, yeah. So this is that, and you can convert everything from one base to another base. There are some rules. Okay, so from any base to decimal conversion, meaning how you do it is that suppose you have a digit, so suppose you have a number something a2, a1, a0, point something, something like this. Okay. So what you do is base r. So you multiply it with the base r power, increase the power when you are moving from left to right. Okay. Sorry, right to left. Okay. That's how you do it. This is basic example. And then I want you to observe one thing here. This observation you see. So what is this? One, 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 one. So 1111. What can you see from this? 1111 means that it is A. It is simply what? It is simply A. You can say that. It is 7, okay? It's not 8. It's sorry, 111 is 7. 11111. Just 4 ones is 15. So if you make a generalized assumption, it will be like 2 power n minus 1 for somewhere for a question where you have so many number of ones. Just you have to count the number of ones, continuous ones, and do this math, and you will get the answer. Okay. Then you have the combinations. Okay, this is the combinations. For 2 bits there is, you can write 4 combinations. For 3 bit you can write 8 combinations. For 4 bits you can write 16 combinations, that is 2 power 4. Okay, then for every thing, so let's go with the new thing, which is logic function. Any logic function can be written in the form of two forms, which is SOP and POS, that is sum of product and product of sum. So sum of product, SOP terms are called min terms, and POS, product of sum terms, are called max terms. Okay. So you can represent any logic function in either of these two terms. They can be equivalent to any of the forms. Okay, you can write them in either of the forms, it's fine. So depending on your use you do it. Okay, then you have this. So this is basically how it works actually. So yeah, so for in min terms, no, 0 is a bar. Okay, for 0 you write it as a bar, you keep a complement out there, but for 1 you write it normal. But in max term it's different, it's exactly different. For 0 you represent a, for b represent this. But the difference is that in sum of products it's producting, and in a product of sum it's a sum. Okay, so that's one thing you need to remember. And then it's simply like this. Okay, so it's not like, it's like not like exactly the statement which I said that min term is exactly opposite of max term. It's not exactly the same. uh Not necessarily. Okay, it's not necessarily like that. You can represent both of them in either of ways. Okay, then let's go now and see some logic gates. Okay, so for logic gates we have not gate. So this is the first not gate. Okay, we have so many gates like not gate, and gate, or gate. Okay, NAND gate, NOR gate, XOR gate, XNOR gate. So let us discuss about each of them in a bit detail. Okay, if you want more details, you can ask doubts in the comment section. I'll be free to respond to you. Okay, so for the NOT gate, yeah. So NOT gate is mostly used, okay, in any implementing any logic. So it is used for inverting equation, inverting anything. Okay, then it's also called a negation gate. It's also called complement gate. Okay, complement logic. So if you put a NOT gate, give input as 0, it complements that. That is, it negates that and it inverts that and gives you the opposite of that, 0 and 1 and 0. Okay, a and a bar. Okay, So this is that. So here you need to understand one thing. In the logic gates, in every circuit, so in every circuit, for a given input, an output comes after a certain time. That is called the top ED. Say that is called top ED, which is propagation delay. Propagation delay means the time it took after getting an input to the output, the time delay that happened during that process is called propagation delay. Okay, we need not discuss that detail about it, but if you want, I will make a small video about it. I do have it in notes, but I did not include it. So yeah, so this NOT gate, when you put it in feedback, let's see another concept which is basically important in gate aspects. Okay, which is feedback. So for a circuit, if you feedback meaning you simply connect the output to again to the input. So that's what feedback is. So if you implement this for a NOT gate, okay, for a NOT gate, if you implement this, if you put two NOT gates, okay, for two NOT gates, what happens is if you input zero, it becomes one at the first NOT gate, then it becomes another. Again it becomes, so if you input 1 it becomes 0, then it becomes again 1, and this one is carried again to the input, so it becomes again 1 0 1. So what's happening is whatever input you are giving, the same output is coming. That is, it's acting like a buffer, right? It's acting like a buffer. Also you can say that a basic memory element. Okay, yeah. So this happens when even number of NOT gates is present. Okay, when even number of NOT gates is present, the frequency is 0 hertz. Okay, and it acts as a bistable multi-vibrator. You say this because the state diagram for this, time chart diagram for this, is like a square wave. Okay, it's like a square wave. It's simply like, I'll show you. Wait, it's simply like wait a second, I'll show you. Uh, it's simply like this. It simply generates square waves like this. Okay, so this square waves, so it's stable at every point of time, so that is why you say that. Okay, then it basically acts like a memory, as I said. So if we see for the same thing, the same feedback thing, if we see for uh the NOT gate, if we have odd number of NOT gates, so what's happening is this. See this time chart. So at first we have two top ED, right? So two top ED means uh propagation delay is 2. So how it came? So here you see, we kept 1 as input, we got 0 as output, right? If we draw this, okay, so this is the chart for that time chart. Okay, so during this whole period, input and output, okay, the T on and T off, all this period combined you call T. So how much units are there? 2 units. So it's coming as 2 top PD, 2 propagation delay. So if you have 3, the same becomes 6, right? So the same becomes 6. You have 3 units of that, so it becomes 6. So if you generalize it, you get the formula as the frequency formula. To calculate the frequency, you get it as 1 by 2 into n, which is where n into top ED, where n is number of NOT gates. Okay, and it works only at odd number of NOT gates. Okay, so if you generalize it, you get this thing which is called astable multi-vibrator. Astable multi-vibrator means as the state is not stable at both 0 and 1. So the state is not so what's happening really in this place is that if you suppose you take 3 NOT gates. Okay, so at this point it's 1. Okay, at this point it's 1, and then here becomes it 0. Okay, then it becomes 1, then it becomes again this thing comes here. Okay, I'm talking about feedback. Okay, so here what happened, it became 0, right? Again 1 0, then this 0 is being passed, so this 0 becomes here, 0 comes, then it becomes 1, then it becomes 0, then it becomes again 1. So you can see this. So what's happening is it is basically an inverter. It's basically an inverter, right? So whatever you give, the same output will not come. So it's an astable multivibrator. It generates a square wave, and it acts like a clock generator. You will see about more about this clock in sequential circuits. Okay, then free running circuit ring generator. Okay, so this is this. Then let's quickly discuss about AND gate and OR gate. Okay. So AND is basically, if you want to understand, it's basically intersection. Okay. And OR is union. So what's intersection? Intersection means common. Union means addition. Okay. Union means including everything. Okay. So this is a shortcut for things. Okay. Zero into anything is zero. Zero plus anything, you can have anything. Okay. One plus anything is one. So yeah, you remember these things. It will be helpful in for you in Boolean algebra and all. Okay. Then let's see about AND gate and its symbol. So you represent AND gate in this form. Okay. In this form, and you can also say that it's A intersection B. Okay, then we have the truth table. Observe the truth table. If you have input as 0 0, that is A into B, 0 into 0, which is 0, 0 into 1, which is 0, 1 into 0, which is 0, 1 into 1, which is 1. So you get 1 only when both of them are true. Otherwise you don't get it. Right. Yes, that's what I'm talking about. So if you say this is called the floating terminal. Okay, this is called the floating terminal. At this place, if you fix a input that is 0 or 1, and there you give the same 0 and 1. So what you get is at 0, that is 0 into 0, 0 and 0, 0 0 0 0 1 0. That is whatever, irrespective of it, it's disabled. The output does not change irrespective of the input. So here control 1 enable. So by giving 1 you get 0. By giving 1 1 you get 1. So you are getting the same result. So it's basically enable. Then this AND gate follows commutative law as well as associative law. Right. So whenever this question might not come, but it's just for understanding purposes. So if A and B is a NOT gate and the A is A ka min term A's min term is given and B's min terms are given, then you can basically do it by A intersection B. Okay. Then you have OR gate. OR gate is simply A plus B, which you can write as well as A union B. And yeah, then you have the truth table. The truth table says that, see, 0 plus 0 0, 0 plus 1 1, 1 plus 0 1, 1 1 and 1. Okay. So this is basically it, and it follows commutative law as well as associative law. And the diagram for this will be this to represent this. Okay. So yeah, one more note regarding gate. Okay. So in gate questions you might see something like uh, TTL and ECL. Okay. Whenever TTL is mentioned, TTL means the floating terminal, which is khali, that is 1. Okay, high, it will be high. So yeah, whenever ECL is mentioned, the floating terminal will automatically be 0, that is low. Okay, then you have NAND gate. NAND gate means it's simply a combination of AND gate and NOT. So the same NAND gate can be written, rewritten as bubbled OR. Okay, you can compute it via Boolean algebra, you will get same thing. Okay, they both are same. Okay, it's same but different. Okay, that meme, you know that, right? Yeah. Then we have the truth table. The truth table is simply inverse of that. And then you have enable and disable commutative law and associative law. It follows commutative law but not associative law. So here the same principle is followed, but the opposite of that. Okay, then you have NOR gate. So in NOR gate, it's exactly the same principle as NAND gate. It's not plus OR. Okay, Uh, it is also the opposite. Like you can represent the bubbled and as NOR gate. Okay, so it also follows commutative law, but it does not follow associative law. As simple as that. And NAND and NOR gates can be used for universal logic creation. Yes. Then we have XOR gate. XOR gate. Yeah. XOR gate symbol of representation is this thing. Okay. Then you represented it with this symbol, and it can be written in SOP as A bar B plus AB bar. The same thing can be written as A bar plus B bar into A plus B. Okay, this is that. And then the truth table. It's you have to remember this. This truth table is simply like if it's same, it's zero. If it's different, it's one. That is, you can simply say that it's anti-coincidence logic. Anti-coincidence logic. Okay? Yes. The same thing can be written. Same, zero. Different, one. Right? So if you interchange this, A0, A XOR 0, A. Then A XOR 1, A bar. Okay? If you generalize it and rewrite things like this, you can remember a trick for this. Okay? A XOR A is 0 because they both are same. Anti-coincidence. Right? Anti-coincidence. So so it will be 0. Then if you do again for 0, it will come as A. And if you could do it for again for A XOR A, 0 XOR A, it will become 0. Right? Sorry, A. Right? It goes on like this. Okay. So you can generalize it as if even number of A's are there, XORs, then you get 0. If odd number of A's are there, when performed XOR, you get A only. Okay. Remember this. And yes, one thing you have to remember is this truth table of XOR gate. It is that the truth table of XOR gate is simply very much useful when you go towards adders subtractors, and at that point you will require this. So remember this, it's 1247. Okay. The explanation is basically if you have to write an explanation, it would be like, so you can see this. You see, everything is same, you get 0. Even if you see here the trick is odd number of ones wherever it comes. Okay, odd number of ones wherever it comes, it is 1. So here odd number of 1, 1. Even number 0, odd number 1. Even number 0, even number 0, odd number 1. Okay, simply remember it like this. Okay, then this 1247 you have to remember A XOR B XOR C is 1247. You have to remember this. Okay, as I said, it is an anti-coincidence logic and also called inequality detector. Okay, then you have XOR gate. XOR gate is simply represented in this form. The not not a bubble is kept at this point. Okay, at this point a bubble is kept. The equation for this would be a bar b bar plus ab, or in POS form it is a bar plus b into a plus b bar. Okay, this and here the truth table, it is exactly opposite of XOR gate, which is coincidence logic. So if your inputs are same, you get 1, that is high. Okay, the same thing can be written like here like this, a XOR a is 1, right? And a XOR a bar, which is different, which basically means 0. Similarly, you can write this like that. Okay, and here a generalized form is A XOR A is 1, 1 XOR A. What happens? 1 XOR A, sorry, A XOR A XOR A. That is 1 XOR A comes A, right? So, yeah. So, for even number of A's, you get 1. For odd number of A's, you get A. Okay, understood? Yes. So, the same thing. And X NOR gate follows commutative and associative law as well. And even XOR follows commutative law and associative law. Okay. So, but there is a small difference in here. A small thing you have to take note of, that you can convert XOR gate into XNOR gate simply by making a bar here. Okay. So if you have AX nor B, if you want to convert it into XOR, you can simply put a whole bar, or you can simply put a single bar as well, or you can put a single bar here as well, or you can put two bars and still you can call it like this. So yeah, similarly for XOR you can convert into XNOR by simply putting both, by simply putting a single, by putting a single, or by putting a double. It will be still be the same. It's like whenever you remove the switch, whenever you remove the bar, you change the symbol. Okay, remember this. That's it. So the NAND gate can be NAND and NOR gate can be represented as universal logic. You have to remember this. So so let's see how many NAND gates it will take. For a NOT gate, for implementing a NOT gate, it's simply like this: one NAND gate. For an AND gate, you implement an AND gate which is A B whole bar, and again if you implement an AND which again goes A B whole bar again bar, then means bar gets cancelled and you get A B. Okay, so how many NAND gates? Two NAND gates. So that is it. So for OR gate, it's basically you take two single outputs A bar into B bar. So, okay, A bar into B bar whole bar, which becomes A plus B. Okay, it's simply like that. Then for XOR only, you cannot apply your basic logic. So for XOR, you have to remember this whole diagram. You have to remember this structure at least. You have to remember because this structure is very important for you. As whenever you are trying an XOR, you will have to do it this way to have a smart and efficient thing. So here it is four NAND gates. Okay, it's four NAND gates. Then for XNOR, it is same as the XOR till this part. Okay, till this part it's the same as XOR. From here on out, just this extra gate is there. Okay, just the extra gate consumes your another thing. Okay, just that extra gate. Okay, then we have so for NOR gate. So for NOR gate, it's what? Four NAND gates. A bar, B bar. Again, A bar into B bar, whole bar. Again, A plus B. Again, another which comes as A plus B whole bar. Okay. So till here it's AND logic. Okay. Till here it's sorry. Till here it's OR. Okay. Till here it's OR. You know the OR, right? We saw the OR. So what was OR? OR was 3. Okay. OR was 3. The same thing till here OR was there. Okay. Till here OR is there. After this OR, again you put a NOT gate and you get the answer. Okay, that's it. Yeah. Then if we see the same thing for NOR gate as well, it comes like this. Okay, the same thing can be designed from NOR gate as well. And to summarize this and to remember all of this, I have made a table. So if you had waited this long, then you will be able to see the table as well now. This is the table, summarized table. So there's a trick to this as well. So I'll tell you. First, let us see this. Okay. So you have to write things in this order only. Okay. In this order only you have to write. Otherwise, you cannot remember the trick. So the trick is, so you write NAND and NOR. Okay. So first order, the same order you have to follow. What order we followed? Not and or. Okay. The same order we learnt as well. Okay. Remember that. Not and or. So in NAND and NOR, in both of them, for a NOT gate, for implementing a NOT gate, you require a single NAND and a single NOR. Okay. So if you have to make an NAND, okay, NAND from NAND, okay, and from NAND, it's simply NAND and NAND. Okay. NAND means A into B whole bar. Again, if you apply an AND, A into B whole bar, again whole bar, which is two bars, which gets cancelled. Okay, cancelled out, and you get AB, which is simply A and B. Okay, so that is how you get this. So again, if you have this OR, for OR you did the same thing. You took A and B separately, A bar into B bar, again another NAND gate, another. Okay, that way you got three NAND gates. Okay. Similarly, if you observe this part, okay, just these two parts, okay, these two parts and these two parts, if you observe, what's happening here is both of them are interchanged, okay. This comes here and this comes here, okay. Remember this? Yeah. See this? The same thing is happening here as well. Both are getting interchanged. The same thing is here as well. This happens only when you write it in this way. Okay. So for it's like for NAND, sorry, for and OR, it's like this: 2 and 3, 3 and 2. For XOR, it's 4, here it's 4. For XNOR, here it's 5 and here it's 5. For NAND, it's the same 1. For NOR, it takes 4. The same from NOR to NAND, 4. From north to north, it's 1. Okay, remember this? Yes, this is the trick for that. I hope you liked it. So if you want more such things, I know it was very slow. I could have covered it very fast as well. Mm, I'll try to be more active and more better in the next video. So please do tell me if you actually liked it. Okay, if you tell me to go in detail about a topic, that's fine. I will do a deep dive on that. And if you prefer any language, specific language other than English as well, you can tell me. Like I can speak in Telugu, I can speak in Hindi as well. So if you want certain parts of explanations, or if you want certain videos on Telugu and Hindi, okay, in Telugu and Hindi on certain topics, I will be doing them as well. Okay, so see you in the next video. We'll be talking about Boolean algebra. Okay, so Boolean algebra and some part about the implementing universal logic with NAND and NOR gates. Okay, implementing that and finding number of NAND gates and NOR gates. So there are some questions regarding that in the GATE exam, although very less frequently asked, but sometimes it will be asked for 1 marks or 2 marks depending on the complexity of the question. So yeah, so let's see them at the next session. Yeah, so if you want me to speak not only English in English but a combination of Hindi, Telugu or such things, please do say. And yes, thank you.